Alright, well, we're Team High Z. I'm Ben.
I'm Joe.
And our project was a park assist system that would ideally help you for parallel parking and avoid situations like this. Oh, it's red on here. Okay,
anyways, on startup, the distance should be displayed on the LCD screen in centimeters.
Yeah.
We also have the LEDs lighting up as kind of like a gauge to light up based on how close you get to something. Also, you should be able to toggle between two modes of displaying distance and velocity on the LCD with the button press button 0, and you can change centimeters or inches if you press button 1, and this works in velocity or distance mode, so you can get centimeters per second or inches per second.
And we're also using an infrared proximity sensor. It has a transmitter and a receiver for the reflected signal, and then it measures the intensity and outputs the voltage. And that's what we're using to do these calculations. These are block diagrams for the hardware. It's actually pretty similar to the function generator, except that this SPI is being used to communicate with the analog to digital converter, and so it's reading in data instead of sending out data, and that goes up to this proximity sensor. The rest is pretty much straight from our other labs. Yeah. This on the right-hand side is our software block diagram, and so we're using a timer to refresh the screen so that the new distance or velocity is displayed every time it interrupts. So we initialize the timer, the LCD display, start timer, enable the interrupts, and then we have the SPI communicate with the analog to digital converter, and then it gets in that data, and then it checks for these conditions of whether the button is, there's a button that converts the units from centimeters to inches, and that will toggle if the button is pressed. And then if the mode button is pressed, then it will do either distance or velocity calculation. The velocity calculation we did by having it store the old distance reading and then the new distance reading, and then dividing that the difference in the distance by the time in between, and then along and then after that one is data, it moves back over and gives that that whole sequence all over. And so Joe is going to start to talk about this design.
I just want to say, basically, the trickiest part about getting the hardware to work was with the analog to digital converter. So, like another group mentioned, we have to send it. You have to trick it or something. Send it.
Yeah, send in the dummy data in order to read out. So, but otherwise, it's pretty similar to the code that we use in the function generator. And so, a lot of this hardware is pretty much the same. From what we used for the previous labs. Here we have our functions descriptions, which are also pretty much the same. The new ones that we have is volts function, which will get the value from the analog to digital converter, and then the distance and velocity functions, which will either calculate the distance or velocity respectively. And so pretty much our design. This is our this again.
So yeah,
supposed to be red, but
everything works. We really wanted to get the hardest part about designing the velocity and the distance was the fact that we have to have 2 points in the velocity to calculate velocity. So if your sample rate is too fast and you're not going fast enough, then it thinks that there's no distance is passed, and conversely, if your sample rate is too slow and you're moving too fast, it thinks that no distance is passed. So you have to find a medium ground. So
basically it was a trade-off between whether we wanted it to update the velocity at a faster rate and be more inaccurate, or update it at a slower rate and be more inaccurate. So we opted for the slower rate with higher accuracy.
And this, on the background of the slide, is the curve of the voltage to distance for the sensor. And so it says it goes up to like 150 centimeters, but out here the change in voltage is so small for like 10 centimeters that we really couldn't get that good accuracy.
Yeah. We picked our range a little bit closer to here so we could have more consistent data. The problem with the centimeters is that the centimeters are smaller than inches, obviously. So when we increment a single centimeter up here, sometimes we have little to no change in the voltage output. So our centimeters the range for our centimeters isn't as large as our range for inches measurements.
We also had to design like a debouncer kind of thing for the voltage, because any little reflection or something from a side would have the voltage spike and would change the distance or velocity dramatically. So we had to design a little thing that would catch it if it tried to flicker back and forth. No, we didn't average. We would just run like a spin cycle to see if it changed again within a certain amount of time, and then it would signal us this value.
Yeah, and as far as, like I said, integrating the system was pretty similar to how we had it for the previous labs, except for the analog to digital converter. And for that, we just had it connected to a voltmeter and or a voltage supply, and then had a multimeter connected to that, and just calibrated the input voltage to what we wanted. And to connect the sensor to it, we were going to do some voltage divider circuits to get it right. But the datasheet actually said that it could use anywhere from 4.5 to 5.5 volts in the Nexus board supply that, so it just worked right off the bat. The only thing was that the connector that it wants to use, we couldn't find that, so we had to break off. We had to cut off the top part of the plastic connector and just soldered wires onto that. But it just hooked right up into the ADC, and its swing, as you can see, goes just below 3 volts, so it's within the full range of the analog to digital converter. So it came out pretty nicely. It's pretty clean. And so yeah, that's pretty much it. Unless you guys have any questions. Show you, like, when you get too close it starts filling up, and then when you get too close it'll flash as like a warning that you're about to hit the car or something. And so this button can switch it from centimeters to inches, and so it does the same thing basically. And then we have this other button switches it from distance to velocity mode, and so if you move it like that, it'll just tell you basically how the speed.
We chose to update it every second.
Yeah, that's
nice
that's the
medium time.
refresh rate.
So it lags a little bit, but if you move at a constant speed.
Yeah, and you can kind of see, like, one of the ways we tested it was to have we had 2 pieces of paper like this, and then if we picked it up it should display the difference between those. And then so this once again converts it from inches per second to centimeters per second. That was one of our design changes, was we originally had it miles per hour and kilometers per hour, but that wasn't, we figured these units were better for the ranges that we were dealing with. So this does the same thing, and then this gauge will show the distance regardless of what.